This lesson is about the electric potential. And the goal of it is to understand how the electric potential compares to electric potential energy. And in fact, electric potential is one of the concepts that is closest to what we deal with in electric circuits, which is the reason why we're introducing it now. And also, you should be able to use then the principle of superposition and calculus to determine the electric potential of complex charge distributions. Here's an example of what the electric potential entails. You're very familiar with batteries. The positive and the negative terminals of a battery are at different electric potentials. And the potential difference, the positive potential minus the negative potential, is what gives us the voltage of the battery. And it's that potential difference that drives current. So positive charges want to go from an area of high potential to an area of low potential, which is how batteries drive current. Let's go back to the definition. The electric potential, and we'll denote this with the variable capital V, is defined as the electric potential energy per unit charge. So if we have a test charge Q0 in the electric field of a point charge Q, then we can find that the electric potential V of the point charge Q in the center is going to be the electric potential energy per unit charge, so it's KQ over R. This is the electric potential of the point charge with a charge size Q at a distance R from it. And conversely, if we have our test charge Q0 that is sitting a certain distance at a certain point where the electric potential is given by V, then the electric potential energy of the charge Q0 will be Q0 times V. So, an important thing to understand here, the electric potential and the electric potential energy are not the same thing. And in fact, the relationship between them, between the electric potential energy U and the electric potential V, is the same as you have between the electric force F and the electric force and the electric field E, where the electric force is the charge times the electric field, and we now know the electric potential energy is charge times electric potential. U and V are scalars, so the electric potential energy and the electric potential are scalars, and so they're easier to deal with than vectors. And just as we have with potential energy, it is the differences in electric potential that are important as opposed to the value of the electric potential itself. And we always, as a result, measure the electric potential relative to some reference point. So we denote the electric potential with capital V. The units for measuring electric potential are volts, also shown by capital V. And 1 volt is 1 joule per coulomb. And if we go back to our example of the battery, the voltage, or the difference in electric potential for the battery, tells you how much work the battery is doing to move 1 coulomb of charge from the negative to the positive terminal. So a voltage of 1.5 volts tells you that to move 1 coulomb of charge, the battery is doing 1.5 joules of work. So the battery has to do work to move charge from the negative to the positive terminal, so that then whatever electric circuit the battery is connected to can use that energy to run. So a positive charge in the circuit will want to move from an area of high potential to an area of low potential to decrease its potential energy. And this is how we get an electric current. So let's take an example of a difference in electric potential. Let's say that we have a charge of 3 times 10 to the minus 7 coulombs, and we're moving it at a constant speed from one plate with a potential of 3,000 volts to another plate with a higher potential, 17,000 volts. So we have to do work because we're moving from an area from a lower potential to a higher potential. In other words, the electric field in this case is doing negative work. We are doing positive work. So how much work is involved in doing this? So here's our solution. This is the difference in potential energy, 14,000 minus 3,000 volts. And then the work done by the external force, us, is the change in potential energy, which is Q times dV, delta V. Q being the charge and delta V being the potential energy difference. The potential difference, not the potential energy difference, but delta V is the potential difference. So then we get that the amount of work done is 0.0042 joules. So as I pointed out, the amount of work done by the electric field in this case is the opposite, is negative of the amount of work done by the external force. So now let's take a look at a charge distribution and look at how the potential of a charge distribution looks like. And as you by now know, we can use the principle of superposition to determine the electric potential of a charge distribution by summing the electric potentials of the individual charges. So for a simple point charge, the electric potential is kQ over R. If we have a collection of charges, say in this case 3, the total electric potential at some point away from them will be the sum of the electric potentials due to the individual point charges. So then each of them is going to be kQ1 over R1 plus kQ2 over R2 plus kQ3 over R3, and that's our total electric potential. And of course, if you have a much larger number of charges, you'll be summing over all of them. So a key difference here with respect to how we do apply the simple principle of superposition for electric field or electric force is that because the electric potential is a scalar, it is much easier to deal with it and to calculate the electric potential at some point away from a charge distribution than if we had to deal with vectors and then to see how the various vectors add up. So now let's look at this example of 3 charges a little bit more closely. So let them all have equal charges of 3 millicoulombs. And we know the sides of the triangle now, they're 5 centimeters. And we asked to calculate what the electric potential here is now in the middle of the triangle, in the plane of it. And also then how much work would have to be done by the electric field in bringing a charge of 5 millicoulombs from infinity to this point P. So let's take the first part of the problem first. So using the principle of superposition, we know that the electric potential at point P is going to be the sum of the electric potentials due to each of the individual charges. Because they are all equal and because P is in the center of this triangle, we just have that as going to be 3kQ over R, where R is this distance from the vertex to the center of the triangle. So we know the side of a triangle. How do we find this distance? Well, this is an equilateral triangle, so the angles are 60 degrees. So then the half angle is 30 degrees, and we can find R from the Pythagorean theorem here. We know that, or just using trigonometric relations, we know that d over 2 divided by r is going to be cos 30 degrees. So then we can find r as d over 2 cos 30, or it's d over square root of 3. So now we can put what we have found for r in here to get the electric potential. So that's this. Ke here is the Coulomb constant K from before. So then it's going to be 3 times kQ over r because we have 3 identical charges. We already found an expression for r as d over square root of 3. So this is 3 times square root of 3 kQ over d. And then when we put in the numbers for the Coulomb constant for the individual charges and for the side d of the equilateral triangle, we get what the electric potential is in the center of the triangle. the individual charges were in microcoulombs, in fact, as opposed to in millicoulombs. I will correct this in the final version of the slides. And then, how much work do we do? How much work does the electric field do? Not we, but how much work does the electric field do in bringing a distant charge of 5? This will be microcoulombs again, because this is 5 times 10 to the minus 6. This is not milli, this is micro, to the point P. So the work done by the electric field is a negative of the change in the electric potential energy, which is minus Q, for Q now being the charge that we're bringing in, the charge coming to point P, of the difference time of the electric potential of point P and infinity. So this is 0 because we're infinitely far away from the charge distribution. So then the work done by the electric field is just going to be minus Q times the electric potential at point P. So Q is 5 microcoulombs, not millicoulombs again. And we found that the electric potential at point P was 2.8 times 10 to the 6 volts, which is also Newton meter per coulomb. So the total amount of work done by the electric field is minus 14 joules. The next example will be of just 2 charges, but now the question is to find a more general expression for the electric potential anywhere in the xy plane around these 2 charges. And for this, there's a separate video solution of the problem. And we'll also, in fact, look at what happens if the 2 charges not necessarily have the same sign, but if they have opposite signs, like we would have for an electric dipole. So far, we have been discussing collections of individual point charges. If you have a continuous charge distribution, so a case like this, for example, a positively charged cylinder, you would have to, again, you would use the principle of superposition, but now you again use integration to integrate over the entire surface or volume of the charge distribution, so that then you get an expression for the electric potential that way. And a final example of a continuous charge distribution now, we have already looked at the case of the charged disk. Or maybe we've actually looked at a charged ring, but now we'll consider a charged disk. And we'll see now what the electric potential is some distance away from the center of the disk on axis. And we'll use what we have learned so far. So the question is, if we have a total charge of Q on the disk, and the disk has a radius of A, what is the electric potential some distance x away along the axis of the disk? And so here is how we go about solving this. The electric potential at point P is going to be the sum of the electric potentials over all individual components of the disk. And now for ease of analysis, what we'll consider is that the disk is comprised of concentric, very narrow rings, because we have already solved the case of for a narrow ring before, or we have encountered the case for a narrow ring before. So let's consider a narrow ring of thickness dr. And we'll say that this ring, the entire ring, carries a charge dq. So all points along the x-axis will be at the same distance from any part of this narrow ring. So they all will be at a distance of square root of x squared plus r squared, where r now is the radius of this narrow ring. So then, it's easy for us to write an expression for the electric potential at point P just due to the narrow ring. It's going to be k dq over the distance from the narrow ring to that point P, which is square root of x squared plus r squared. So this is for the narrow ring, but we want to be integrating this to get the whole disk. So what we do to get the electric potential due to the whole disk is we change the size of our ring from 0 to the total size of the disk. So we integrate r, the radius of the ring, from 0 to a, the radius of the disk. So now the electric potential at P is going to be the integral over the integral sum of the electric potentials of all narrow rings with radii from 0 to a, which is what this expression shows. Now we have a little bit of a complication here. We're now, our integration variable is q, so we have dq, but we're integrating over radius. So we have to somehow express q in terms of r, or dq in terms of r. So we are given the total charge on the disk, and we also given the area of the disk because we know its radius. So we can actually get its charge surface density, call that sigma. It is the total charge on the disk divided by the area, so it's q over pi a squared. So then the amount of charge in a narrow ring, that was dq, is the surface charge density times the area of the ring. And the area of the ring, because it's so very narrow, it's going to be its circumference times its thickness. That is a key expression to remember. When we're dealing with a very narrow ring, the area of that ring is going to be the circumference times its thickness dr. So 2 pi r circumference times thickness of the ring dr. So this is the area of this narrow ring, and its surface charge density sigma, so that then the total charge on that ring, dq, is going to be sigma, which is q over pi a squared times 2 pi r dr, and when you put it all together, you get 2q over a squared r dr. So now we've expressed dq in terms of dr. So we go back to our integral. So then the electric potential Vp becomes k dq over x squared plus r squared. This is now integrated from r equals 0 to a. So now we put our expression for dq in here. So taking out constants in front of the integral, we get qk over a squared, and under the integral we have 2 r dr over x squared plus r squared, square root of that. So it's going to integrate to 2kq over a squared times this expression, where this expression, or the evaluation of this integral, we get from using a table of integrals. So this was the most complex example that we showed of how to determine the electric potential due to a continuous charge distribution.